without further ado, I introduce Peter.
Thank you for that elegant introduction. And thanks very much indeed, host. It's a really great pleasure to be here again, and I think we should all really thank Sarah, who really put this meeting together, so we should give her a round of applause. This is indeed the 11th year of these meetings, and also the fact that we have Mikhail rather State because of Sarah's generosity in giving a charitable donation herself. And so indeed we had Wayne McGregor last year, which was a fantastic meeting at SWC, and so we're very much looking forward to the event today. And so and thanks again to Jonathan and everyone here for organising this event. So I was being irritated before that we had taken a year and a half to get into our centre. I hadn't realised in fact I was postponing our sort of brain death by a year and a half. So thank you for pointing that out. Good. So I want to talk about some work that was done by a postdoc, Zed Kurth-Nelson, who now works at DeepMind, together with Ray Dolan and Gareth Barnes, who works on MEG, the MEG expert in UCL in London. So here the context is about reverse replay during human problem solving. So we're trying to look at what we're trying to do is to understand what happens as subjects are planning in a complicated domain. We want to try and get some sense of some of the cognitive processes that are going on by decoding information from MEG. So let me tell you the story of how far we got on along those lines. So I'm going to start off about a third of the talk, probably or so, talk about a preliminary investigation that we did, which was to try and understand what it would be like to try and decode information from MEG in the first place. And so here I'll tell you about a task that we worked on, which was comes from something from Daphne Shahami and Elliot Wimmer, called sensory preconditioning. They did an fMRI study, we did MEG. And then I'll talk about a task, a rather complicated task, that actually, even more complicated variant of a task, which actually, together with John Reuter and Quentin Hughes, we've been involved with earlier, which induces complicated planning behaviour in our subjects. And then we then used MEG whilst they were planning to try and understand the process they were going through. So we'll talk a bit about behavioural evidence that they really engaged in complicated planning in this case. And then also talk about what we actually found at MEG, which is, as it turns out, not exactly what we hoped. But you'll see, so in a sense, we're still one step back from really capturing some of the planning processes. But I think what we found was interesting along the way, at least I will try and convince you of that fact. Okay, so let's start with sensory preconditioning. So this is a paradigm in which what you do is you induce a relationship between two essentially arbitrary stimuli. You then associate one group of those stimuli with reward, and you come back to see, has that had an effect on the way the other stimulus is processed? So the way this works is you have three phases of presentation: an association phase, a reward phase, and a decision phase. And in the association phase, you create a relationship, usually just a temporal relationship, between a set of stimuli. Here we're showing faces, body parts, and places. So we chose those because we hope we'd be able to decode them in MEG, because we hope they'd be represented sufficiently differently in the brain. You generate an association between those particular faces and then, in this case, a particular set of arbitrary, in this case, fractal patterns. So here you can see a set of fractal patterns here. And so in this task we have, actually we showed before, but we imagine there are two faces, which are going to be associated with two fractal patterns, two body parts, two fractal patterns, and two places, two fractal patterns. Then during a reward phase, you take the fractal patterns, the arbitrary patterns, the things we didn't expect to decode, and then you associate some of them with reward, stone written, so PANS, and some of them with no reward, so no outcome at all. So, as I said, there are two phases and two fractal patterns. So one of those phases is associated with a fractal pattern which is associated with reward, and the other phase is associated with another fractal pattern which is associated with nothing. You then come back in a decision phase and ask subjects whether they have learned something about the stimulus, so the face in this case, that was associated with the fractal that was associated with the reward. So you can ask them, do they prefer the fractal that was associated with the reward to the one that wasn't? So in this case, you might expect they will prefer that because it was associated, they prefer this one because it's associated with reward. But you could also ask whether the stimulus, the place here, which was associated with this fractal pattern, which is a reward, was preferred to the other one. And the phenomenon of sensory preconditioning is that in fact that's what you see. They prefer the stimulus. Subjects prefer that stimulus. And you can imagine two ways. Yeah.
The decision phase, is there any instruction at which you prefer, or
So in the decision phase, you give them pairs, you ask them to pick one. You can also ask them how much they like, if you give them a single stimulus, say how much do you like it. And there are a number of different ways of doing it. And then, but yes, that's the way it's typically done, choose one fractal over the other. They know, you can do it in different ways. You can tell them whatever happened to that fractal pattern, you'll get, we're not going to tell you what it is. So it's done formally in extinction. So during the extinction, during the decision phase, they're not receiving reward as far as they know.
And they're aware of that.
Yeah, exactly. But and you have because there's quite a lot of stimuli here. It's not I present it in this nice sort of top-down way. The subjects are usually a bit more, they don't know what the question is, of course, when you ask them that, what the question you're trying to study. And you can imagine two ways of doing that. One is during the decision phase, they could see this picture and say, well, that's associated with the fractal pattern, and that's associated with the reward, if they prefer it. The other is that during the reward phase, presentation of the fractal could bring the stimulus that it's associated with to mind, in the case of this place, and that might then induce learning during the reward phase, which is then reflected in the decision phase. So in the paradigm that we adopted from Wimmer and Shahami, it's actually a fairly weak, behaviorally weak form of sensory preconditioning. But what they had done was to collect fMRI evidence that indeed it was their ability to use fMRI to decode the fact that subjects are thinking about places rather than, or that they could decode places rather than body parts or faces during the reward phase, that was predicted of the extent to which they preferred the fractal pattern, preferred the stimulus that was associated with the fractal pattern associated with the reward. So it looked like all the action was happening in the reward phase, not the decision phase, in terms of the way the association worked. So we did the same. We did use a very similar design to them. In fact, it was pretty much the same design. And then one of the phenomena you see here is that this particular way of doing sensory preconditioning is rather weak. So you can see what we're looking at here is the choice they would make. So when they're asked to pick between the two stimuli, they express like a moderate preference for what's called the direct stimuli. So the SD, they're the ones that are directly associated with the reward, the fractal patterns. And there's no net behavioural preference for the picture, so the decodable stimuli. And the same is true if you look at how much they like some measure of liking of the outcomes. But that masks individual differences, so some of them they like more, and that's what Wimmer and Shahami did, was to say, is the extent to which they like a stimulus more at the outcome, one of these indirect stimuli, is it associated with what happened during the reward phase? And you'll see that we did exactly the same thing in this case of sensory preconditioning. Okay, so what does the MEG signal look like when you present one of these patterns? So these are the patterns we're showing, these are the pictures we're showing during the association phase. We're going to build ourselves a decoder during the association phase. And this just shows you the evolution of our particular sensors. I think we have like 374 sensors, this is a standard MEG machine. Actually, MEG technology is changing, but this is still the old stuff with SWIDs and so forth. And you can see that you get an evolution of the pattern following the presentation of the picture, and it's different for different patterns in various different ways. And that difference might make you think, well, maybe you can use some sort of machine learning method to try and decode which stimulus they're seeing. So what we did is to use support vector, just a regular, nothing fancy, a support vector machine with a linear kernel, to decode, to predict what the category was of the stimulus that was shown. So not the particular stimulus, but just the category. Is it a face or a place or a body part? And this shows the performance of that. Again, so it's baseline is a third, because there are three categories. And you can see that the performance as a function of time since the presentation of the stimulus during this association phase. And what you see interestingly is there seem to be two rough peaks, one around a couple of 100 milliseconds and one around 400 milliseconds. Of decodability. Now this isn't generic, so there's some lovely work from Sichi and Ord Oliver looking at many different sorts of stimulus categories, and there you can see that there are some subtle differences in the timing. But then for us, that was what worked nicely. And you could ask whether there was actually anything different about the structure of what's decoded at the 200 millisecond point versus the 400 millisecond point.
So why it was down? There is a window that you use by the...
What we do is we divide the time into, we divide the MEG signal into 20 millisecond time bits and build a separate classifier of each of those each of those time bits. And it just so happens that, and indeed we did a statistical test to show that it really does get worse in between. And you'll see there may be a reason why in fact just now. So what we did was to to try and look at what might be different between these two, we did representational similarity analysis. So that's a way of just saying how similar is the activity, a correlation matrix essentially, of the activity in the MEG signal at these two time points, 200 milliseconds, 400 milliseconds, for all the stimuli. Now, for technical reasons, we had 4 phases, 4 revolving parts, and 4 places. And so here, this is just how similar is the signal. What you can see is that at the 200 millisecond case, there's no interesting pattern of similarity, apart from the fact that you get this sort of similarity down the diagonal, which is what you expect. But at 400 milliseconds, you see that the pattern of similarity makes it look like it's category specific rather than stimulus specific. So all the phases are more similar to each other than they are to all the activity in the brain is more similar for all the phases than it is to all the other things and so forth. So it looks like we have 2 different things being decoded here. This is more stimulus specific, this is more category specific. And another piece of evidence in favour of that is that if you look at we then said, what happens if we try to decode the fractal patterns during this association phase? So the fractal patterns don't come in categories, it's just one category of fractal patterns. And you can see that, in fact, you see a peak of decodability here at again, the 200 millisecond time, so the individual time, not the 400 millisecond time. So that 400 millisecond peak goes through. So it looked to us like what you're seeing, and of course this is the advantage of MEG. At the scale of fMRI, it's very hard to see things that are happening quickly, although obviously people are always trying to enhance the speed of fMRI cases, but in MEG we get this nice fast signal. Okay, so then what we could do, so that all happens during the association phase. So then during the decision phase, now during the reward phase, when we're presenting the fractal patterns and the rewards, we can now ask whether or not we can see any reflection in the MEG signal of the stimuli that were associated with the fractal. So here we have a place associated with a particular fractal. We can ask, are we capable, when we show that fractal, of decoding the stimulus type, in this case a place, that was associated with the fractal during the association phase? Now, what these plots show is what that looks like when we're... what you have to worry is that because we have this evolution of the signal following the time that the place is shown in the first place, we can ask, we get different classifiers at each different time point. That's why we have this different capacity here. So this shows the time, the classifier built as a function of time since the stimulus during the association phase. So this is, you think of this as different times along this axis after seeing SI. And this says, but of course, we can get a recapitulation of the brain activity that we see 200 milliseconds after the plate is being shown. That could happen maybe 400 milliseconds after the fractal is shown here. It takes a while for that to develop during the time that the fractal is being shown, rather than during the time, of course, that the stimulus is being shown itself. And that's what you see. So here, if we look at the time since this fractal was shown, so that's this axis here, you can see that after about maybe 300 or 400 milliseconds after that, you get a recapitulation of the activity associated with the type of stimulus that was associated with this 200 millisecond peak after that stimulus was there. So basically the stimulus-specific peak, it gets recapitulated about 300 or 400 milliseconds after the fractal is shown. We made a mistake in our design, we only realized afterwards, which is we had a fixed time between the fractal pattern and the reward. So it means if we then look after the reward comes, after the reward is presented, you can see that now, actually almost contemporaneous with that, just maybe just a little bit afterwards, you see a recapitulation of this 400 millisecond peak around the time of the reward is there. But of course we don't know if that's because there's a fixed time here, we don't know whether that's a fixed time after the frontal was shown or is it a fixed time after the reward was shown. We don't have any insight to that because we made a mistake. And so there's a significant difference between these two. So what that means is that during the reward phase, in fact now we get a little insight into why sensory preconditioning might be behaviourally very weak in this case, because the aspect of the stimulus that's being recapitulated around the time of the reward is actually the aspect of the stimulus which is category specific, not stimulus specific. And remember, in the decision phase, we've had one place associated with the fractal with reward, the other place associated with the fractal without reward. But if all that subjects are remembering at the time of the reward is being presented is the place, then of course that's not then they're just going to learn that places are sometimes associated with reward. And so they're not going to therefore develop a preference between the two different places that we presented in the first place. So what we then did was to say that even though in general at the time after the reward, we don't see much recapitulation of this 200 millisecond peak. So anything, there's nothing strong about this 200 millisecond after the reward, the thing which is actually specific to the type. We can nevertheless do what Wimmer and Shahami did and ask, is there any relationship between how strong the recapitulation of that 200 millisecond peak is, either the one which is actually stimulus specific, and the subject's preference for that particular picture? Indeed, that's what we see. So what this shows now is essentially the p-value for the correlation between how much you see this 200 millisecond peak, and then how much the subjects prefer the fractal pattern associated with that. So you look down here, you can see that there's a nice big peak there after about the reinstatement of this what we call this 200 millisecond component, which makes sense because it's that component which is specific to the stimulus that was being presented. So the reinstatement of that component is consistent with the fact that subjects prefer the associated. Okay, so this is essentially preconditioning. So it's a little slice of what you might think of being model-based behavior. So what we're going to argue later is that model-based reasoning is where you build some sort of model of the world, and then you're either planning with a model, or you're using some aspect of how you know the structure of the world is to think about what might happen in a context. So in our case, what makes it model-based is that the subjects have learned this predictive relationship between the patterns, between the fractal patterns and the original stimuli, and then at least in the reward phase, that's being recapitulated enough that they can then develop this preference. We found these two time factors. Well, the reason we did this study is before doing the main planning study I'll talk about, is we want to know what sort of things should we look for in MEG to be able to do it. So we found these two relevant time slices by doing this multi-voxel or multi-sensor pattern analysis. Actually, we did everything in sensor space, we didn't try to project it into the brain. This 200 millisecond one, which is object specific, and the 400 millisecond one, which is category specific, and we found that related to the behavior. But of course, preconditioning is not a very interesting sort of planning behavior. It's much more, it's just really about simple associations, and we were interested in more complicated planning. Okay, so then what we did was to talk to our subjects with the following task. So this, excuse me. There are 6 states labeled S1 up to S6, and then like each of the sensory stimuli before, these states are represented by hopefully decodable stimuli. So there's a French horn, hands, animals, garlic, things like that. So subjects have extensively learned, and this is we've done quite a bit of work with John Reuter and others looking at other versions of this. It's a particularly difficult variant of this. So subjects have extensively learned how they could move between the different states. So although they never saw this top-down map, but what they did know is the tree, they had 2 actions with the tree, and one action would go to the garlic, here, and the other action would go to the cat. At the garlic, there were 2 actions, one goes to the chair, one goes to the French horn, and so forth. So they knew the structure of the maze, and we knew that because we could ask them questions like, you're at the tree, tell us the sequence of moves you do to get to the, 3 moves you do to get to the hand, or something like that. So although they may or may, we don't know what structure they built in their heads for the way that this looked, they certainly did not see this top-down view that we're providing you with this node. We knew they knew what was happening. Now, in this task, the way we ran it is the following. We would put them in a location, one of these locations. Let me do this. Each of these locations then is going to be associated with a certain amount of reward. And those rewards were changing on a trial-by-trial basis in a way that was partially hidden to the subject. So what's going to happen is they're going to, as a result of planning, they're going to run into the garlic, let's say, and so S2, which is shown by the colour here, red, this red thing here. When they ran into it, they would discover what the current reward being provided by the red stimulus is, by the garlic stimulus is, and then it takes a while before they come back. The next time they come back, then it will have a different value. So all the time, these values are changing, and our subjects are going to have to learn what the current value is to doing their planning. So, and these values can be positive or negative between plus and minus 5 units. So what's going to happen is, we're going to put them at a starting location. So we start with garlic, and then what they're going to have to do is to plan a sequence of 4 actions and they get 60 seconds to do the planning. They can choose to terminate that early, maybe they stop after 30 seconds if they've had enough. But and having planned it, they then have to enter the actions very quickly. And so they enter the actions by like up, down, just the way the arrows work, although of course it doesn't mean that's just the two arbitrary actions at each state. They have to enter them quickly. Then after doing that, they then, because we want to tell them what the current reward value is for the states, they then have to enter them again slowly. So they've entered them here as being the things, let's say down, 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 up. They then have to enter them slowly. They then get to see what the current reward rate is associated with that number. And then at the end of it, they get the total reward associated with the places they get to. Now, to really make them do planning on a trial-by-trial basis, we add an extra complication, which is what these call these neg states. We tell them that if they land on the chair or the hand, this guy or this guy, then they'll get the reward, the current reward associated with that chair, and then the total reward they've accumulated so far will then be inverted, go to minus the value it had. So for instance, you could get a lot of reward by planning your 4 steps, get lots of negative numbers, really bad numbers, and then land at the end on one of the neg states, let's say the hand in this case, and then all your rewards again get inverted, you get positive reward. And so what we're trying to do is really force them to plan. We want to maximize the chance that they couldn't use model-free or simpler strategies because there are too many complexities. So we have flexibility in the reward values. We also have this flexibility on a trial-by-trial basis, which is the next stage. And so we had to filter out quite a lot of subjects before we put them in the scanner because quite a few of them were unable to do well enough in this task, as you might imagine. I don't think I would be able to do it myself, but we won't go there. Okay, so what does planning look like? What does behaviour look like here? So here, what I'm showing is how long they use for that 60 seconds of doing planning. So here, these subjects are ordered, I think there are 12 subjects ordered by their mean planning time, so the blue guys are the fastest. You can see that some of them will sit there and plan for quite a while, some of them will plan more quickly. This shows the statistics of earning, so the colours here are the same as the colours here. And in fact, there's a slight negative correlation between how quickly you go and how much you earn. So basically, if you go quickly, then you tend to earn more. So perhaps there's obviously some difference amongst the subjects of how good they are. Maybe the ones who are really on the ball can think quickly and also get a lot of earnings. But it's a fairly weak correlation, as you can see here. In any event, the subjects were clearly able to get some substantial, this is the statistics of how much reward they got. So our subjects are clearly somewhat capable of doing really well. Indeed, if you debrief them afterwards, you can see that they're thinking they could present it fairly, they could of course do a very good map of what the structure is, that we knew they knew that. But also they would report their frustration of just missing the neg state at the end, and so getting lots of positive rewards for them having it all inverted. Okay, so we had behavioural evidence they did planning. So then what we could do is to fit different models of what planning there might be. So, and then the sort of models you might have is, well, they could just choose completely randomly. So in fact, those subjects would also be thrown away before we put them in the scanner. You could imagine doing proper full-depth planning. So if you have 4 binary actions, that's 16 possibilities. So there's not so many, but it could be possible. We also looked at simpler strategies where they do some sort of Q-learning. Now, because of the change, things like the neg state, it's actually very hard to get Q-learning off the ground in this case. So we offered us a couple of sort of cheating versions of Q-learning themselves, or some sort of greedy thing where they just go to the place where they think currently has the biggest reward. So what this shows, sorry, slightly busy, but focus on this, yeah.
So are you better off getting big rewards and avoiding the neg state, or small rewards and getting it?
So since you can predict it, since you're told where the neg states are, you can just make it just depends on what the current reward values are. So you just think, given I know that there are neg states, it's just a 16-state planning problem with some optimum path. And for this, if you start regarding this particular case, what the best thing to do will just depend on all these current values and on whether you can get to the neg state, right? Because you can't guarantee to end on the neg state from everywhere because the systems may not just not work out that way. So you could just sit there, think about your 16 plans, and we'd say which one is best. And indeed, when you do that, so what I'm showing here is big scores. So we built the various models of how they could go about doing their planning, and this shows essentially our capacity to predict the choices that they would make based on these different classes of models. So the first 4 are for these the variants of sort of reasonably optimal planning, maybe with some temperature, so they have some random stochasticity in their planning. And then these other, if their behaviour is purely random, and these other things show variants of Q-learning, where the model-free basis. And what you can see is the black these black areas are taking account of the extra parameters. So there's like the thick penalty, the complexity penalty, and so here low is better. So what you can see is that all across the subject, and this is actually showing all the subjects because I'm so busy, you can see that across the subject there's certainly evidence that they are doing something more like optimal planning than they are doing these other Q learning things. But in fact we know, and indeed with John and Quentin, we've done quite a bit of work in a much simpler variant of this task, looking at other sorts of structures that they might be building for doing the planning. So in this case, we just used the simple version, just said, let's imagine they're doing this sort of planning, and we are focusing here more on the MEG analysis to try and understand if we could see what was going on in their heads as they were doing this planning themselves. And so thinking that maybe we would see some of the sequences of states that they were thinking about, right? So they started with garlic, maybe we could detect that they were going from garlic to chair as they were maybe related to the choices they actually made. Obviously, that's not exactly what we saw. Okay, so our behavioural conclusion is subjects are planning but imperfectly. So imperfections are great for us because we could then look for selective effects that had to do with what they actually did as opposed to what was optimal. So as ever, it's the things which go wrong which actually are most revealing. So we have this explicit planning coexisting with model-free strategies. And then, we know different ways of doing planning. You can do forward search, you can do backward search, you can build these 16-state trees and so forth. And there are also stochastic methods of doing search, like Monte Carlo tree search, so different ways of doing other sorts of ways that the reinforcement learning literature has come up with for thinking about planning. And we could look for all of those in the behaviour, if we could, in the MEG signal, if we could decode the states of things that they were thinking about. And so that's why we wanted to do MEG. Okay, so now in this case, we built a slightly different sort of model to try and decode the MEG signal. So again, we have these 6 different stimulus categories, and here we actually, and what we try to do is to train logistic regression models to decode what they're thinking about. Now, we didn't know that they would only be thinking about one state at a time, so we didn't want to say, we're going to force you to say it's the garlic and not the chair, so we didn't want to build a predictive model like that. We just want to say how much they think about the garlic, how much they think about the chair, and then there's no extrinsic competition between thinking about those two things. So actually during a phase at the end of the task, in fact, rather the beginning, we showed them, we had like a cover story, we showed them the individual patterns that we built ourselves, these regularized logistic regression models to try and work out whether we could predict what they were thinking about. And you can see here that we can do a reasonable job. So here, this shows that the predicted probability of the stimulus, the stimulus we're thinking about, so when we knew we were presenting the stimulus S1, this is what our regression model showed about S1, so forth and so forth. So you can see that we had a reasonable way of predicting what it was they were thinking about when we knew that they were presenting the stimulus.
This is one trial or average over many?
So this is the performance on a average over many trials. This is just the average performance of our classifier across all the trials. And we presented a number of trials. We did cross-validation. So we build the classifier based on I can't remember what the fold was. But we build the classifier based on build the regression model. Some fraction tested on the others. So we're reasonably sure. We did a lot of work to try and convince ourselves, actually consensual preconditioning work already, that we weren't fooling ourselves with statistics, so we can go through the permutation test and so forth for that.
Are they seeing these before they do the main task?
So in the sensory preconditioning, we built it before. In this case, we actually built it, as it happens, we built it afterwards, which might have been a mistake for reasons. If you ask me that question at the end, I'll tell you why that might be a mistake. So here, remember, we're just looking at the predicted probability. We could then say what would happen if we chose the best of the one which gave us the highest predicted probability, and then we would be more than 50% correct, which is good for their stimuli, because it's much bigger than chance. So then what we could do is to look at the 60 seconds, well, the up to 60 seconds in which our subjects were doing this planning. So there's nothing interesting on the screen at that time. We tell them, you're starting at the state garlic, and then we write that in a letter. We don't even show them the picture of the garlic. And then we could just run our classifiers, run our logistic regression models, and say, what do they report about how the brain's state during this planning time is like the different states that we see. So what you see here is the output of these output of these regression models. So we split time into 10 millisecond chunks. and you can see that you get a reflection of what there's something going on in the brain. It looks like we get different of these states seem to come up in different ways over the course of this time. And so these arrows just showing cases where you get these peaks of these signals. Something we don't understand is that it looks like the predictive probabilities are much stronger during this planning time than they are during the time that the stimuli themselves are being presented, which seems completely weird to me. We've not ever really gone back and we've not been able to understand. We were not able at the time to understand why that should be. So here the predictive probabilities make it very small. Here you can see the predictive probabilities are getting very high during this time. In any event, what you'll see is you get this nice temporal pattern evolving of the way that subjects are thinking about different states. And so what we'd like to do is to say, does the things that we can decode, the fact they're thinking about these different states over time, does that relate to anything about the structure of the task? That would be a sort of zeroth order thing. Does it relate to the actual stimulus, the actual stimuli, the actual choices they're going to make on this particular trial? Does it overrepresent the starting state, if they start with garlic, for instance, or whatever the state they start at, and so forth. Okay, so remember, subjects they can choose when to stop. So we chose some consensus time, I think like 35 seconds or something, which incorporated most people would think for at least that length of time for most of the trials. And then we now have just the output. We get a big matrix, which is the output of our classifier, this 10 millisecond time bin, as a function of time from the start of the trial. And so we have, this is just 35 seconds of what that matrix of decoding looks like. So we analyze 603 trials. Okay, so then so the first zeroth order question is, does this relate even to the rules of the game, right, to the task itself? So a very simple way to look at that is say, here's the transition matrix for the task, right? So if you imagine you choose actions at random, so do it equally often, so if you have two actions in these states, then from state 1 you can get 50% probability to state 2 and 50% to S5. So here you get a transition matrix which shows you the statistics in the task. So you could imagine that if you were representing, if you think about what it's like to go forward through the task, through this transition matrix, it means if you were thinking about state S1, which means you have a strong activity at S1 here, then in whatever the granularity, the temporal granularity of your thought would mean that at the next time step, we'll talk about what that time step might be, then you should be thinking either about state S2 or state S5, which means you should see a nice peak here for state S1, and then at some time step later, you see a nice peak for either the S2 model or the S5 model. That would be the perfect way that this matrix would reflect the structure of the forward structure of this transition matrix. So what we could do is to take the state, our current representation, multiply it by the transition matrix, this forward transition matrix, and off. So that gives us a matrix which predicts what they might be thinking about if they were thinking about the structure of the maze, and then just say, does that new matrix, which is now should be sort of one step forward in the maze, does that relate to what they were actually thinking about at some later time in the structure? So they're essentially going to take this forward matrix and just correlate it at different time lags with the matrix of what it was they're thinking about. And that would mean if they're thinking through the maze, then you would see this high correlation at that time. Similarly, if you want to go backwards through this transition structure, you just look at the backwards matrix, which is the transpose of this transition matrix, which goes backwards. And again, you get a new matrix which would reflect them thinking backwards through the maze rather than forwards. And you think it might be strange to move backwards, but we know from hippocampal work, for instance, that you see what's called reverse replay. So there in the hippocampus, I'll show you some evidence later, or some data from other people later, that because with play cells you can detail what they're thinking about. And it's known that at various times, maybe during quiet wakefulness or during sleep, you see either forward sequences where subjects are going forwards in space, or you see backward sequences where subjects are thinking, where the hippocampal activity is moving backwards through the notional space of the task. Okay, so we have these matrices, and then just compute the cross-correlation between these matrices at various different time lags to see if there's any relationship, any evidence that they are thinking forward in this way. So what does it look like when you do that? So what you're seeing here is this lag. So we don't know what the temporal granularity of thought is. We don't know how long it takes them to think from one state to the next. So we're going to look at many different times. So we're then going to have to correct those. That's what this shows here. And then what you're seeing here is every single correlation between these different states. So here, this is and then because of the symmetries in this structure, we can say there's a SI and SI plus 1, they're always related by the forwards. SI and SI plus 4 is always related by a backwards transition and so forth. So what you see is there's a large amount of autocorrelation in the signal. The signal doesn't change that quickly, which isn't so surprising. But that's going to give us a big problem, because it's going to turn out to make life complicated for us. That's shown by this green. So it says if you're thinking about state 1 at time t, then you're pretty much thinking about state 1 at time t plus delta, where delta is all these different lags. So you have a very slow autocorrelation. But nevertheless, you can look to see, is there anything selective about the other stimuli you might be thinking about? And what it turned out, and though what this is showing here, is as a function of different lags, there's a time point at which there's a statistically significant difference between the amount you're thinking forwards and the amount you're thinking backwards. So of course we'd love to be able to independently look at forwardsness and backwardsness, but it turns out we can't with this strong autocorrelation. So all we can look for is there more forwards or more backwards at that time. And it turns out that although it looks like a very small signal, indeed it is a small signal, there's actually significantly more backwardsness than forwardsness at around at a temporal granularity of about 40 milliseconds. So I realise this isn't so convincing. Let me show you something which may be a little bit more convincing. So what we can do here to do statistical testing is, it turns out there are 28 sort of non-confounded permutations of the states. The other ones are confounded because of the rotational symmetry in this maze. And so we can test against those permutations to see if we can do all our procedures with the rotated matrices and see if we are more statistically, we see a stronger backward sequenceness than in our real matrix than we do in the one where we do these permutations. And you see that's true at around this 40 milliseconds, and then it goes back to baseline. Then it's not statistically significant at other times. You can look across subjects, and you can see that for many of the subjects you're seeing a peak at around this 40 milliseconds. You can also look at the average across participants over trials. So now this is the trial. This is showing the lag, the temporal lag. And indeed, you can see that consistently across trials. It's not as though you only see it at the beginning or the end or whatever. You see that there seems to be some significant effect in which they are, which around this 40 milliseconds they are thinking more backwards than forwards. So what that means is that there's a backwardsness to the way they're thinking through the maze. So this is the transpose of the transition matrix, at a temporal granularity of about 40 milliseconds per state, which is therefore the granularity of this internal plan. You can look at now, so here we look just at one step, right? So you just went one step through the maze, but you could instead go 2 steps or 3 steps or 4 steps or more steps through the maze, and then see what that looks like. And what you can see is that for leg 3 and leg 4, we still see a strong effect around the same 40 milliseconds. But by the time you get to leg 5, then that effect has got away. And indeed, in this particular case, we asked subjects to plan the 4 steps. Now, of course, we don't know that that relates to it, because this is just generic about moving back to the maze. The maze only has 6 states, and there are many different questions you might ask. So I don't think that this really necessarily relates to the questions we asked of them. At least it shows that they are thinking some number of steps. Yeah.
So what is the green 10 to the minus 8?
What's the... Sorry?
10 to the minus 8.
So this is the difference. So sequenceness is the difference in correlation between forwards versus backwards. So here we're looking at
alarmingly small.
It's extremely small, right? And so that's why we have to worry about a lot about what statistical testing is. So the way we did the testing here is just permute the states, which means that if you permute the states, it means that you don't expect correlation except for, so that's why there are only 28 unique permutations because of all the rotations. And so our biggest potential p-value is 1 over 28, which isn't very big, right? Very small, I guess, if you like it. And so it's a very small effect. So I completely agree with that. And that's why we did these other tests to try and convince ourselves that they were true. So the fact you see it consistently across trials, the fact you see it reasonably consistently across subjects, and the fact you see it consistently across these not just 2 steps, 1 step more, you also see it for 3 steps, but not for 4 steps. It also seems reasonable. So it's not that we're always guaranteed to find it. We don't find it when you look at beyond some value. But I agree, it's not the strongest thing you'd like. If you want to see what that looks like in a more microscopic view, just give you we just pulled out a couple of examples from this matrix. So you can see here there's a little burst of activity. So this is a bit like the sorts of things I said we'll see in a minute. So the campus, you see they're going from state 4 to state 6 to state 5 to state 1. So hopefully if I got that right, so we go to state 4, we go backwards to state 6, whereas we go backwards on that arrow, we go backwards on the arrow to state 5, and then backwards on the arrow to state 1. Here's another example, and so forth. So what the thing that's being picked up is the idea that there are these backward sequences, and so of course you can find some particular examples of those. But this isn't statistics; this is just eye candy. You can ask what the time, why 40 milliseconds? And so I think that certainly in the canvas we know that it's an autonomous it's an autonomous system in the sense that it's not choosing the time relative to behavioural time. So we know, for instance, in slow wave sleep you see an acceleration of a factor of 10. In REM sleep you see an acceleration of a factor of 1.5, rather less. You can ask, does this relate to anything in the time step of the task? And the answer is, well, not really. So the sort of things in the time of step of the task are, how long, when we're rendering, when they're actually entering the choices, and there's a sort of fading process that goes from one stimulus to the next. That takes a second or two. Then the entire transition takes rather longer than that. And so we're seeing something much faster than that, much more like you'd see in the hippocampal replay. So here's an example from work from Lauren Frank's lab, just one of many, many examples. So here you have a rat running along in a linear track, so therefore you have directional place fields. So that means you can ask sensibly about whether you have forwards or backwards places. What they've done is record from many different cells. So here you're seeing a bunch of cells, and then they've color-coded them by their positions on the maze, on the linear track where they fire most strongly. So you can see that when the animal's running forward, you just get this nice forward drift, and from that you can of course do decoding. And what you're seeing is times at the beginning, before the animal starts running, or at the end of a little episode. Then what you can see is the reactivation of a set of cells both before and afterwards. And if you look in more temporally fine detail at that time, you can see a reactivation, which is, in this case, you get a piece of forwards replay. At the end, as it happens, you get a piece of backwards replay. And that's been well observed in many labs, so David Foster, Mike Wilson's lab, and many others have observed these sorts of replay events. And indeed, it's been suggested for a long time that replay might be a really good way of going about doing offline planning. So in reinforcement learning, there's a mechanism called Dyna, which was invented by Rich Sutton in the 90s, suggesting that you might recapitulate some of the state that you've been in, and then use that to essentially do offline planning so you can generate a better plan subsequently. So it might be that what we're seeing is something associated with that. So people have speculated about whether that should be a forward nurse or a backwards nurse.
Is this related in your mind to the backward propagation in control or in reinforcement?
Exactly. So that's what people like David Foster suggested naturally. They said, okay, what you're doing is a way of propagating backwards, like the dynamic programming essentially. That has not been proven at all. And indeed, in Foster's work, there's a lovely paper by Pfeiffer and Foster where they showed that the choices that subjects made, in this case were rats running he had a very nice task where rats would go out to explore and then come back to a known location. And so they would know half the time where they were aiming for. And then you could look to see whether or not there was any relationship in the forwards or backwards, in this case forward sequences, and the actual trajectory the animals took. And what this shows is indeed there was. So you can see they're sort of projecting forwards in their domain was related to the path they actually take. So that's an example. That's essentially what we hoped to find originally, that when they were planning, we'd actually see something about the forward choices they're really going to make. We didn't see that. We saw something which is this more generic sort of backwards planning. It is known that if you disrupt sharp wave ripples, so you disrupt the time when some of these events are happening, then you can disrupt spatial behaviour. So they probably are functional to something, but exactly what has yet to be called. Oh, yeah, sorry. Yes, okay, what's done. Okay, so this is, I think, one of the first appearances of replay, the sort of replay process in humans. And so, to be fair to us, unreasonably fair to us, it took a long time in the rodent hippocampal world to go from the observation of replay to the cases where you could see it having a behavioural effect. So that was, like the work of Pfeiffer and Foster and Lauren Frank and so forth, looking at that. So for things like navigational consequences. So we don't yet know in our human studies what that looked like. The autocorrelation, this very strong autocorrelation, made it hard to assess forwardness. But of course, in a sense, I'm reporting a failure to you, which is we didn't actually find any correlation with the real plans, what we really hoped for, the plans that they were doing. So we tried, the favourite part of, in any paper that Zeb writes is all the things that we tried and didn't work. So you have a nice description of all those things. So we tried looking for all the things you would think about, all the simple things you think about for this, to overrepresent the start state, if you see overrepresent the trajectory they actually choose. So we didn't see any evidence of that, but it's early days, and I think that we could design a slightly simpler task where we could get more people to do it, get them to do it for longer. And I think it'd be really exciting to try and look for some of the other structures we know about in planning, chunking, and so forth that we can see. So I'm really excited about looking at this in the future. So thank you very much.